di Milano, and please, welcome.
So, good morning. Really, it is a pleasure for us, for both of us, to having been invited and to be here in person, because we feel that it is, in many cases, it is necessary, even in spite of the distance, to have some face-to-face connections. So my presentation is on more or less on the subject that we are dealing with. That is, we at Politecnico di Milano, we are doing, at a smaller scale, I would say, a similar job as you are doing with the construction of strong motion data sets from physics-based simulations. It is a kind of I feel that it is a kind of complementary work, but maybe there is actually a room for very interesting synergies. Our tool for calculations is speed. That is our own, so we developed during the past, say, at least 20 years, this spectral element code for numerical simulation of seismic waves in heterogeneous media. It has some features that are very similar to what Dave has shown, the SW4 software. It is also open, and it has been actually used by several groups, actually. It is based on the construction of models, relatively large-scale models of different areas. As you will see, we have dealt with many different areas, and this may be also a complementary thing with respect to what has been done here in California. So with the different kinematic models for the faults, and okay, our computational resources are very powerful with high performance computing, not as powerful as Dave has shown. So still we face a problem of enriching our numerical simulations with high frequency. So I will spend just this slide, this comment to recall that in our case, so typically our results from the numerical simulations are at low frequencies, so long periods, say beyond a T star, say 2 hertz, 0.5 seconds, and to construct the low frequency part, the high frequency part, the low period, we use an artificial neural network that is trained on records. So we we match the result of the physics-based low frequency physics-based simulation in order to fit as closely as possible, or with a certain tolerance, this artificial neural network spectrum that provides a good physically based or based on the records relationship between low and high frequencies. As I said, eventually we are now still processing many of the simulations that we did in many parts, areas of the world. You will see that there is nothing here in California, because we know that you are doing a much better job than we could do. But as you can see, we have a rich set of simulations in Italy, of course, also because of the number of earthquakes that we had in the past, say, around 15 years. So there has been a good opportunity to make validations, but we have also some validations in other parts of the world, Europe, France, Netherlands, Iceland, Greece, Turkey, Japan, Kumamoto, some earthquakes from China, Mexico City, a small earthquake in Mexico City. So it is a relatively wide set of simulations, and we decided eventually to put together the results of these simulations, or at least a selection, within a open data set. We have called it the BB speed set, broadband speed set, that contains a significant amount of these simulations, more or less those that are shadowed in this plot. Of course, this is something that may grow with time, and we did some attempts to validate the results, the values of the spectral ordinate that we have. We did it by considering a data set of records that in terms of magnitude and distance is as close as possible to our, because for obvious reasons we are typically dealing with say near source conditions because of the size of the model. So as you can see here, the NES is a near source data set that was collected based on the worldwide records, more or less in the area that you see indicated here. That is the one that precisely was shown as a domain where the availability of records is relatively still insufficient for a complete understanding of the problem. And of course, the blue dots are instead the results of our the couple, the pairs magnitude and distance that are present in our data set. We have checked that the distribution, so the check is that within the same range of magnitude and distance, we are expecting to have a similar distribution of intensity measures of ground motion. This is actually the case. As you can see, the distribution of peak ground acceleration, peak ground velocity, spectral acceleration at intermediate and long periods are actually very close to those that are from the records, from the near source record data set. Also, at the right-hand side, the relationship between the 5 seconds, the very long period, and the very short period spectral ordinates are in a rather good range. We have checked a number of things, for example, the pulse periods. So, of course, we are expecting near source to have many signals presenting characteristics of pulses, for example, according to the algorithm by Shea and Baker. And again, the distribution. The red is the record, the near source record data set. With the blue one, that is our own data set, is similar. And also, for example, the variability of the pulse period on the vertical axis with the ratio PGD over PGV is very similar, again, with respect to the strong motion data set NES. Of course, we have many more data available because all in all, we have maybe not so many earthquakes, like 10, 15 within the VV speed set, but many stations available. We have made a number of checks also, especially with this NES data set. We have seen that the within event residuals are perfectly in line with what is from the records. Between event a little bit less, but this is also clear. We have much less earthquakes that are still present in the data set. Let me, probably what I feel a little bit annoyed is this comparison that puts probably the emphasis on some issues that still have to be improved. This is the period-to-period correlation that comes out from the recorded near source data set and our simulated data set. As you can see, the blue line, the broadband, okay, results fit rather well, but still there is a too strong correlation especially between the short and the intermediate periods. This may be related to the way that we construct the short period part of the data set, so probably the artificial neural network should be improved somehow. Maybe having, as Dave has shown, having the possibility to run fully physics-based simulations throughout a wide frequency range, maybe the agreement with the period-to-period correlation from records may be improved. So we have now constructed our own tools for selection of ground motion, tools that may extract both records and simulation in order to do the engineering type of works that we may be interested in, so that you can select records or simulations to fit a target spectrum. We have implemented different data sets, so in the same tool you can select either from the NGA or from the BB speed set or from other near source records, all of them or just one of them. And you can select records with some false characteristics and other features that you can construct. And and we have checked that when the criteria for selection are similar, so both we require the same spectral compatibility, both to records and to simulations, we have typically obtained very similar results in terms of the engineering demand parameters for the structural response. So for example, we have made a comparison, say, given the same target spectrum, the backline, selecting earthquake records from the NGA, the red line above, or from the BB speed set, the blue lines below, in order to fit as closely as possible the target spectrum. Based on that, you can see that there is a rather important difference in terms of the variability. But this is also because the BB speed set is much richer in, say, near source data set, so it is a little bit probably easier to find records that are close to the target spectrum. So we have made some comparison, what are the engineering demand parameters, considering the records from the NGA, considering records from the BB speed set. As you can see, there is almost no significant change in using one or the other set of records. We have then extended, because the previous ones were analysis based on single degree of freedom system, elastoplastic single degree of freedom system. So we are now improving this set of validations by considering more realistic examples of buildings. This is nothing but one of these examples. It is rather interesting to see that if you use two data sets, the NGA and the NGA, the red one, and the blue, the BB speed set, but you use in terms of intensity measure for fragility studies, p-ground acceleration, then you will see that there is a significant spread of the results, a significant spread, because clearly we know the PGA is not a sufficient parameters to obtain reliable fragility curves. While, for example, if one uses as intensity measure to describe the fragility of the building typology an average spectral acceleration, typically between 0 and 1 second, then the agreement is much closer. So you can you cannot distinguish well one or the other set of results. And the fragility curves that come out actually are similar. So I have 8 seconds to say this is something that really we are here also to share these experiences. Of course, the data sets are different, of course, but the objective is very similar, because we also would like to share with the engineering community the set of simulations as far as possible, using similar criteria for validation and so on. But as you have seen, we have made a lot of work from that point of view, and so we are hoping that this could be of interest for you. Thank you very much.
Any question from the floor? Go ahead, Dave.
I'm curious how you define T star as the transition between physics-based simulation and something else. How do you think of deciding what your T star is? Is that based on computational limitations? Is it based on a decision of lack of understanding of the geologic model at a higher frequency? Or how do you think about T star in defining T star?
It is a good question. In principle, our T star is related to the maximum frequency of the numerical model. So typically, we may reach 1.5, 2 hertz. So I have in mind T star values that may be 0.5, 0.75.
But is that based on concern of inaccuracy at higher frequencies, or is it primarily established based on where you want to spend your computational effort?
It is essentially based on the limits that we have on the numerical model. So that it is essentially in order to avoid, to emphasize dispersion, the numerical dispersion, and in many cases also the lack of high frequency that we can put, for example, in the fault model, in the kinematic model. So we have to make a balance between what is the detail that we can reach in the geological model and in the fault model with respect to the also the numerical capabilities. Consider that probably this is also a difference with the case that you are dealing with California. We have many examples of simulations, but in many cases the detail that we have is not as precise as you might have in California. Still, the validations are good, okay? But probably with a relatively low level of detail for this simulation or for this information, it may not be so much meaningful to push towards so high frequencies where the level of information that you have is not so high.
I'll ask an engineering question. So I see you talked about the EDPs, and I see a single degree of freedom model. Is it all based on a single degree of freedom, or you tried something with?
Yes. Actually, I got we made a relatively wide validation process with the single degree, elastoplastic single degree of freedom system. Now, as I said in the very last slide, we are moving towards more
different typologies.
Different typologies, not only the 4-story that I have shown, but there are a number of them, and precisely in order to see the response. So looking at the interstory drift ratio that can come out with one set and another set, in order to construct, for example, to understand better the non-linear response of the behavior. So we are moving in that direction, actually.
Thank you. Any other questions from the floor? We will keep the online questions till the end. So.
Quite a lot of the strong ground motion instruments in Italy are on soft soil sites. So when you're trying to compare your PBS solutions, which I think would require you to invent your own velocity model compared with what Mother Nature sent to the soft soil site that was the actual instrumental record. So how does that figure into making a comparison? And are you comparing on a log scale plot?
Our comparisons are on time histories and in many cases as far as possible time history, Fourier spectra, response spectra. The availability of data, for example, in Italy, of course, the situations may be different. In Italy, we have modeled a lot of earthquakes that actually happened within tectonic basins in the central Apennines. We have made a number of comparisons with the Poplane earthquakes, so in the large sedimentary area of the Poplane, not as large as, if you look at papers, you can access, for example, the paper regarding the Poplane earthquake. It is called Anatomy of Strong Ground Motion. Anatomy means that we have made a very careful time history. We made a very careful time history comparisons, as far as possible, of course, in order to provide, as far as possible, realistic results of the simulation. You will never obtain a point-to-point comparison with the records because you don't have the whole information.
Thank you very much.